Okay, so now we start getting into topics that are um, a little bit more, let's say, troublesome because we are going to deal with a lot of pointers and a lot of dynamic memory allocation, and this is actually a pretty difficult topic, but it's not that hard to get started. So let's take a look. The basic functions that we're going to use are there's just two of them, malloc and free. And the what malloc does is allocate memory, and you pass in as parameter essentially the number of bytes. So what it's looking for is variables of type size d, but almost always if you use an int you're going to be fine. What malloc returns is a pointer to the location where this number of bytes has been set aside just for you to use. And so once you're done with this, once you do whatever you want with this chunk of memory that's pointed to by the return value of malloc, you can pass that whatever malloc returns into a function called free, and it takes care of giving that space back to the operating system so that it can be allocated for someone else or for you when your program runs later. So malloc allocates a little chunk of memory from the heap, and so this is always done. Malloc is always it's only going to allocate memory from the heap, nowhere else. And free gives it back. So what happens if you don't call free? So the thing is, if you don't call free, and if you keep allocating memory, eventually you're going to run out, or your program will stop before it runs out. If you run out of memory, your program will crash, and if it gets to the point where you run out of memory, well, the whole operating system might crash because that's a lot of memory. So to avoid serious problems with memory that's running out of memory, things like that, it's advisable that wherever you see a malloc, you should look for a matching free. So whenever you see a malloc, look for a free, and that's probably a good indication that you are taking care of any memory that you allocate inside your program. You're freeing it, and so you're not going to have what are called memory leaks. Okay, so there's a whole bunch of problems that we run into, but it also makes our programs a lot more flexible. And it's using dynamic memory allocation that allows you to set up dynamic data structures like linked lists, trees, graphs. All of those things are possible because of dynamic memory allocation. So it's a tremendously useful set of functions, malloc and free, but of course with all of that power, you have to be careful too. So here's a simple memory allocation program, a simple program that uses dynamic memory allocation. In this case, what we want to do is that simple thing that we said that we want to do. That is, let's say we have a string, and all we want to do is add something to it. In this case, an exclamation. So we have this 5, 6, 7, 8, 9 character string. Of course, remember all strings have a null termination character, so that's why we declare the string S as an array of 10 characters because we need space for these letters and numbers and space, and also the null termination. So we have 10, and then what we want to do, as we explained in the previous video, is we want to tack on an exclamation at the end of the string. Now in Java, C++, you can do this simply by doing an append operation. So you say whatever the string is plus whatever you want to add to it, and it's that easy. However, in C we don't have any of that, and that's why we have to use dynamic memory allocation. And it turns out in Java, essentially what we use behind the scenes is dynamic memory allocation. That is, you're allocating objects on the heap. So it just so turns out in C we actually have to do it all ourselves or put these things into our functions, And in Java, we don't have to do that. It's all just there, easy and ready for us to use. We can just use the addition or append operator. So let's take a quick look at this. Once again, this is setting up a basic string that we want to append an exclamation to. In order to do that, we have to create a new string dynamically. Oops. And we have to give it 11 characters. That is because we need 9 for these characters, plus a null termination, plus 1 more for the exclamation. That's a total of 11. Okay, so all this does is allocate a chunk of memory, and then the next thing we need to do is copy the string S into this chunk of memory that's pointed to by T. So note here that T, if you were to read this, you want to read this as saying char star is a pointer to character, but chances are, as we've seen before, T is a string. So you want to read this as T is of type string, and so whatever type T is, and it's got to be a pointer, we have to cast the return value of malloc as that type. So in general, this is what you will see. The pattern for malloc is whatever type you have here on the left hand side, you cast the return value of malloc as that type, and you're all set. So then the next thing you do is you treat this character as an array. And so you can go back and forth. You can treat arrays of character as strings or as arrays whenever you feel like it. And in this case, what we're doing is you're copying each element of S. We copy that into this array T. Okay, including the null termination character. And then here's where we tack on the exclamation character at the 9th position, and then the 10th position, T sub 9, which is actually the 10th position, and T sub 10, which is the 11th position, because we started position 0. We finally add on a null termination character, and so if you were to run this program, what you would see is that this will print out the second, this printf will print out hello 248 exclamation. In this case, it won't print out a new line character, so you got to watch out for that. So this is just to show you that we're just printing out exactly what we have, and you might be, when you actually run this, you might wonder why it doesn't give you a new line. That's just because we're not printing out a new line. And finally, at the very end, it's always good to do this, even though in this case it doesn't matter. It's always good that wherever you see a malloc, you want to look for a matching free, even though in this case, the next thing we do after free is exit the program, and whenever you exit a program, all memory that you use in that program is freed anyway. So even though we do that, it's still a good idea to have one free for every malloc, sort of like open close parentheses. Okay. Next up, we'll look at a whole bunch of string functions, and so I'll put that in a different video, starting with strtol, that's converting a string of digits to an integer.